Alright, I'll start off by reading the problem statement. It says we have steam at 250 psi and 700 Fahrenheit steadily enters a nozzle whose inlet area is 0.2 feet squared. The mass flow rate is 10 pound-mass per second, and steam exits at 200 psi with a velocity of 900 feet per second. Also, a heat loss per unit mass of 1.2 BTU per pound mass occurs. Determine the velocity of the steam at the inlet and the temperature of the steam at the outlet. Alright, so here what we have is a nozzle. We notice that the nozzle, remember the purpose of a nozzle is to increase the velocity. Alright, so the exit velocity is 900 feet per second. That means our inlet velocity should be really small compared to that. Also, it increases the velocity by decreasing the pressure. So the pressure we see decreases from 250 to 200 psi. So we'll start by setting this problem up, defining the system. So in this case, the system, we have steam, or in other words water, in a nozzle, where water is a phase change substance and the nozzle is an open system. So that's our system for the sketch. We're going to just sketch the general nozzle shape. So the general nozzle shape has a big inlet area and a smaller exit area. And then the inlet, we're going to call that number 1. The exit, we're going to call that number 2. So properties that we have at the inlet, we have pressure, temperature, and area. And the properties we're given at the exit, we know the exit pressure and the exit velocity. So here's our sketch. Next thing is we define the conditions. So in this case, we have the chapter specific condition, steady flow. It actually says steady flow in this problem. It says that the steam enters steadily, but even if it didn't say that, we could assume that for all of these chapter 4 problems. Then we apply the usual nozzle conditions. So if you look back in our notes, we notice that the usual nozzle conditions are that the change in potential energy is negligible. Also, the nozzle requires no work input. So delta PE and W are 0. And the other typical nozzle condition is that there's no heat transfer. But this problem statement says that there is somewhat of a heat transfer here. There's a heat loss, so we can't neglect the heat transfer like we normally would. But we can neglect potential energy change and the work. Next, we list out all the properties that we're given. So we're told that the inlet pressure is 250 psi. The inlet temperature is 700 Fahrenheit. Next we have the inlet area is 0.2 feet squared. Then we have the mass flow rate is 10 pound-mass per second. So we have m dot is 10 pound-mass per second. Then we have the exit properties. It exits at 200 psi and velocity 900 feet per second. And the last thing is that there is a heat loss per unit mass. So we can include that in our nozzle picture. We forgot it. Here we have Q out. So there's a heat loss per unit mass of 1.2 BTU per pound mass. Alright, all the properties are now well defined, and we're ready to start solving the problem here. So what are we looking for? We're looking for the velocity at the inlet, that's V1, and the temperature at the outlet, that's T2. So we want to know V1 and T2. So again, it may not be obvious whenever we're working these problems, especially for the first time, where these numbers are going to come from. So what we can do is we just go through our step-by-step analysis like we've been practicing for each one of these problems. We start off with the mass balance, and along with the mass balance we could potentially use the mass flow rate equation if it's applicable. And then we go from the mass balance straight into the energy balance, and we analyze the energy balance using the conditions that we defined for the problem, and then we see, is there any way that I can solve for V1 and T2 with that information. So let's start off with the mass balance. We have a nozzle, so one inlet, one exit, single stream device. Therefore the mass flow rate 1 is equal to mass flow rate 2, or we have a constant rate of mass flow through the device. So in this problem, we're given the mass flow rate, and we're actually given information about the area A1. So what we can try to do, since we're given the information about the cross-sectional area, typically that means we can use the mass flow rate equation to find either the mass flow rate, or in this case, we're looking for velocity. So let's see if we can use it to find velocity. Our mass balance says I can apply the mass flow rate equation at inlet 1 or outlet 2. So in this case I would want to use this part of the equation because I know A1, I know the mass flow rate, I'm looking for velocity V1, and then specific volume is a property that we can look up based on the properties that we know at the inlet. So let's take this equation and solve it for V1. That's what we're looking for. So V1, if we cross multiply, is m dot times specific volume 1 divided by A1. So now in order to find V1, we're given mass flow rate, given area, we just need to find specific volume at state 1. So we'll look at the inlet properties. At the inlet, we know pressure is 250 psi and temperature is 700 degrees Fahrenheit. We have water is our system, and it also says that this nozzle, at the inlet we have steam. So we don't have to worry about checking the phase of the water at the inlet. It says that we have steam at the inlet. So we know we also have a superheated vapor at the inlet. So what we need to do if we're looking up specific volume, we just find specific volume at the given pressure and the given temperature from the superheated tables. Another good idea, since we're already looking up specific volume, we know that with the chapter 4 problems we're going to be also applying the energy balance, and energy balance has specific enthalpy as part of that equation. So why don't we go ahead and look up the specific enthalpy as we turn to the tables for specific volume. That'll save us a little bit of time going back and forth between the tables. So we're going to look up specific volume and enthalpy at 250 psi and 700 Fahrenheit. So this table that I have with the properties packet is only SI units. So it's not going to be able to help us here. Let me get out the book, and we can use the book to look up the properties, specific volume and H. Also, I'm going to turn on the light so that we can see the book. So I'm getting my book and I'm turning back to the English tables. I want to go to the one for the superheated tables of water. That's going to be table A4, and then it's specifically table A4E because we have English units. And then I'm going to find the subtable where we see P is equal to 250 psi. So here's my subtable. Pressure is equal to 250 psi. And then I'm looking up at a temperature of 700. So my specific volume value, 2.688, and my specific enthalpy is 1371.1. So let me mark those two numbers down. Specific volume V1 was 2.688. And then the units there are feet cubed per pound mass. Our H was 1371.1. Units on H are BTU per pound mass. Alright, so now we have enough information to solve for the velocity at the inlet. Let's go ahead and do that. And since we're doing English units in this problem, let's go ahead and work through all the units. Make sure there's no weird things going on with the units. So first thing we had was the mass flow rate. That was 10 pound mass per second. Times specific volume, which we just looked up as 2.688 feet cubed per pound mass. Divide that by the inlet area. Our inlet area was 0.2 feet squared. So looking at the units here, I have a pound mass that will cancel out, and then this feet squared will cancel out with 2 of those feet. So we end up with feet per second, which is exactly what we want for velocity. So actually no units to worry about in this case. We can just calculate V1 directly. V1 is going to be 10 times 2.688 divided by 0.2. Our inlet velocity, 134.4 seconds. And we note that inlet velocity is definitely much smaller than the outlet velocity, which was 900 feet per second. Alright, so that is the inlet velocity. Once we know the inlet velocity, we can start looking for the temperature at the exit. Not exactly sure at this point how we're going to get to the temperature at the exit, but we've applied our first equation, the mass balance. So let's apply the second major equation, and that's the energy balance. So our energy balance, we start off with the single stream form of the energy balance for the nozzle. Cancel off the negligible terms from our conditions. Potential energy and work are gone. And then we'll need to solve for Q, delta H, and delta KE in this equation. So in this case, Q we know is related to the heat loss. Right? We had a heat loss per unit mass of 1.2 BTU per pound mass. But heat transfer in the first law has to follow the sign convention, and the heat loss is negative heat transfer. So our Q is just going to be negative 1.2 BTU per pound mass. Next, we can look at the change in kinetic energy, since we know both the velocity at the inlet and the velocity at the exit. So our change in kinetic energy just going to be 1/2 times V2 squared minus V1 squared. We know both V2 and V1, so change in kinetic energy is completely solved for as well. What about delta H? So delta H is just H2 minus H1. And since we have phase change substance, we're going to be looking up these properties in the table. We've already looked up H1. Let's see if we can look up H2. So looking at the outlet condition, or the outlet properties, what do we know about the outlet? We know pressure, and that's it. We know the pressure at the outlet. We don't know anything else at the outlet. So we don't have any other intensive properties. We do know the velocity at the outlet, but that's an extensive property, so it can't help us to set the state. So before we can actually figure out H2, we would need another property at the outlet, which we don't have. So in this case, let's look back at this equation. Looking back at this equation, Q is known, delta KE is known, and delta H, we know H1, so H2 is the only unknown in this equation. So we can actually use the energy balance to solve for H2. That's what we're going to have to do. So let's just solve for H2 from the energy balance. Here we had negative Q out was equal to H2 minus H1 plus 1/2 V2 squared minus V1 squared. This is just the energy balance. Solving for H2, we get H1 minus Q out minus 1/2 V2 squared minus V1 squared. So here, let's go ahead and just start punching in the numbers. We're going to have to do a unit check because velocity is in the equation. So H2 looks like H1 we found as 1371.1 BTU per pound mass. Units on that are good. Then we had minus our Q out was 1.2 BTU per pound mass. Units are good on that. Then we have 1/2 times V2 squared. V2 is 900. And V1 we found as 134.4. For the units on this term, we had velocity squared, so that's like feet squared per second squared. So we'll need to figure out how does feet squared per second squared compare to BTU per pound mass. So what we can do, maybe we can look up something at the beginning of the book. Let me see if there's anything useful in the beginning of the book. Let's see. Alright, not actually seeing anything useful at the beginning of the book. So I can just go ahead and give you this conversion here between feet squared per second squared and BTU per pound mass. This is probably just something we can look up on Google or something like that, or we can try to convert BTU into a different energy unit and then see how it relates to feet and seconds. Alright, I'll go ahead and give us the conversion here. We're going to be multiplying this times, I'm going to have to bring it into the next line. Just multiplying that last term by 1 BTU per pound mass is equal to 25,037 feet squared per second squared. So this feet squared per second squared cancels with this feet squared per second squared, and then now that leaves us in BTU per pound mass. So let's go ahead, we'll calculate H2. H2 here is going to be equal to 1371.1 minus 1.2 minus 1/2 times 900 squared minus our V1 squared, and then multiplied by that conversion factor, we divide by 25,037. So H2 ends up being 1354.1. And that is in BTU per pound mass. One good way that you can check this number if you're a little bit unsure is to just think about what's going on with the nozzle. The deal with the nozzle is that it increases velocity from V1 to V2. V2 is much higher than V1. And it does that by decreasing the pressure, which we saw pressure P1 is bigger than pressure P2. And it also, in the notes, I said that it decreases pressure and decreases specific enthalpy. So specific enthalpy at the inlet was 1371.1, and then that gives us a decrease in enthalpy to 1354.1. So we actually do get that decrease in enthalpy, and the numbers should be pretty similar. They're not going to be exactly equal to each other, of course, but they're not going to be super far away. Alright, so we have H2 now, and once we have H2, how does that help us to solve for what we're interested in, which is actually T2? So going back to our outlet number 2, now we have pressure and we have specific enthalpy at the outlet. So those are two specific intensive properties that are independent of each other. So based on pressure and enthalpy, we should be able to figure out a third property like temperature. So with P2 and H2, we can check the phase. Just a quick check of the phase, we would want to figure out Hg at P2 and also Hf at P2 to check the phase. So let's look at that. So P2 is 200 psi. Going to table A3E, that's the pressure table, and looking up H sub G at pressure P2, here is 200 psi, and if we read across to Hg, we see Hg is 1199.3. So our value of 1354 is bigger than Hg. That means at the exit we still have a superheated vapor or steam. So that Hg that I just read off was 1199.3. And that means that H2 is bigger than Hg2. We still have a superheated steam at the exit. So once we know it's superheated, we can go to the superheated tables and look for a value with a similar pressure and a similar specific enthalpy. So let's go ahead and do that. That's going to help us to solve for T2. Alright, so back in the steam tables, that's table A4-A-4E. Looking for the subtable for pressure is 200 psi. So here's the subtable for pressure is 200 psi. And then we're looking in the H column for something that brackets 1354. So here's a number, 1373.8, and here 1322.1. So those numbers bracket our value of H. That means our temperature should be corresponding into the two numbers here, 700 and 600. So what we can do now, we can just run the interpolation to get T2. So T2 is going to be an interpolation. Those values from the H column that I just said that bracketed our number were 1322.1. Our number is 1354.1. The second table number, the higher one, was 1373.8. And then the temperatures that correspond to this number, 1322, 600. The one that corresponds to 1373.8 was 700. So we can run this in our interpolation program to get T2. So T2 is just interpolating between, let me change the folder here, make sure this works. Right? Can interpolate between 1322.1, our number of H2, 1373.8, 600, and 700. So T2, 662. Not degrees C, that is in degrees Fahrenheit. So this pretty much wraps up the problem. So in some of these problems that we're looking at, let's take a look at the energy balance real quick. In some of these problems that we're looking at, we're given information about delta H, and we can maybe solve for something like the heat transfer or the work transfer. In other problems, we're given the heat transfer, and we use that information to solve for a property at state 2. So this is an example of where we're given the heat transfer, and we were solving for some property at state 2. So it's kind of like the backwards problem for the energy balance. Our final temperature turned out to be 662, and our inlet velocity we found to be 134.4 feet per second.